Welcome. So in this video we will learn all about the infrared spectroscopy. So infrared spectroscopy. Now infrared radiation is actually electromagnetic radiation that we know, and then IR spectroscopy refers to the measurement of different frequencies of IR radiation. It may be falling in the mid IR region, far IR region, near IR region by fluids or other solids, liquids and gases positioned in the path of the infrared beam. Okay, so IR spectroscopy refers to the measurement of different frequencies of IR radiation by fluids or other solids, liquids or gases positioned in the path of an infrared. And but information we are getting, we will able to know the functional groups present in a sample. We can have prediction about the structure, its structure, and also the fingerprint region matches, and again we can identify the compound also. So that is structural elucidation and compound identification. So here it is written structural elucidation and compound identification and quantification. So infrared radiation is electromagnetic energy with wavelength longer than visible light and shorter than the microwave. So we know that electromagnetic radiation, that is electromagnetic spectrum, that is 6 UV-MAR, then this is cosmic ray, gamma rays, X-rays, UV visible region, IR region, microwave region, radio wave frequency. So in this direction your wavelength is increasing, and in this direction of course your energy is increasing, and as well as the frequency is increasing. So here we can see that infrared is having more wavelength, that is as compared to the visible region, and less wavelength as compared to the microwave radiations. So IR is having higher wavelength as compared to the visible light, and lower wavelength as compared to the microwave radiation. Now the main goal of IR spectroscopic analysis is to determine the chemical functional groups in the sample. So basic I will discuss in the coming slide. Very basic is I will explain in a very simple manner in the coming slide. Now different functional groups observe characteristic frequencies of infrared radiation because different functional groups are vibrating at a particular frequency, and if the frequency of vibration of a particular bond matches with the frequencies of IR radiation, then it absorbs it. Its amplitude increases, but the frequency, that is number of vibration per unit time, remains the same. Thus IR spectroscopy is an important and popular tool for structural elucidation and compound identification and quantification. So these applications we will study in the coming slides. Welcome. So in this video we will learn all about the IR spectroscopy. Now if we consider a bond, say we have AB bond. Now this bond seems to be static, but actually this is not static. It is stretching. It is stretching and compressing, showing the vibration. That is mean to say that this bond can be considered in the form of a spring, and this is stretching and compressing, and that is mean to say that it is vibrating at a particular frequency. It is dancing at a particular frequency. That is the meaning. So that frequency is given by 1/2 pi root of k by nu. So the frequency with which this bond is vibrating is given by 1/2 pi root of k by mu. Now k is known as the force constant. So more is the value of force constant, more will be the IR absorption frequency that will be absorbed by the bond. That is, the more stronger is the bond, higher is the IR absorption frequency. Now mu is the reduced mass, that is written as 1 by mu equal to 1 by m1 plus 1 by m2. So this is reduced mass. That is meant to say that if the lower atomic mass will be there, of the atom, which is one of the atom is having lower atomic mass, if we want to compare, then it will be absorbing at higher frequency. If the atomic mass is higher, then it will be absorbing at a lower frequency. So this, from this equation we can have predict the IR frequency that is being absorbed by a particular bond. That is frequency equal to 1/2 pi root k pi by mu, where k is the force constant, more is the force constant, more is the strength of the bond, higher will be the IR absorption frequency. Reduced mass, that is lower is the reduced mass, higher will be the IR absorption frequency, and higher is the reduced mass, lower with the IR absorption frequency. Now apart from stretching vibration, if we have triatomic molecule, like we have water molecule. Now in this molecule, that the vibrations which are shown are known as the bending type of vibrations. Now first is scissoring. In scissoring, what happens is that, so here we can see that if the within the plane, so this type of vibration is within the plane, scissoring is within the plane. this is within plane, and then another is rocking. So this type of vibration, say both H and hydrogen atom are moving in this direction, that is backward and forward. Then this is again within the plane, so this is called as rocking. So this is also within plane. Now if the these heterogen bond, then bending vibrations can also occur in out of the plane. Say if say both the H molecules are coming towards you, then it is called as wagging type of vibrations. Now if one hydrogen is moving away from the that is inside the plane, and then other hydrogen atom is coming out of the plane, that is out of the plane vibration. So these both are the out of the plane vibrations, that is wagging and twisting. This is out of plane vibration. So this type of vibration can happen, and this vibrating frequency is given by 1 by 2 pi root of k by mu, that is the reduced mass. Now if we consider that we are discussing about the IR spectroscopy, and IR is infrared region, and we know that if you that about the electromagnetic spectrum, which is 6 UV, that is cosmic rays, gamma rays, X-rays, UV visible region, infrared region, microwave region, radio wave region. And in this way, in this side, that wavelength is increasing. That is mean to say that IR is having higher wavelength compared to the visible region, and lower wavelength compared to the microwave region. And this is very simple from this electromagnetic spectrum. And IR frequency which we are targeting in this type of spectroscopy. Now and in terms of energy and frequency, we can say that IR radiation is having higher energy and frequency as compared to microwave, but lower energy and frequency as compared to the visible region. So that we can see here. Now if we can want to divide IR spectroscopy into further three, that is near IR, mid IR, and far IR. And then if you want to express in terms of the wave numbers, how we can express it, that this is near IR region lies between 1200 to 4000 centimeter inverse. That is in micrometer terms, we can write it in this way, that 0.8 to 2.5 micrometer. Here also 2.5 to 15 micrometer, and then 15 to 100 micrometer. That is mid ranges from 4000 to 400 centimeter inverse, that is to say 2.5 to 15 micrometer. Now here if far lies, that is for far ranges less than 400 centimeter inverse, that is in terms of micrometer, that can be written as 15 to 100 micrometer. Now mid IR region can be further divided into fingerprint region and the functional group region, that we will discuss in the coming slides. That fingerprint regions lies between 1400 to 400 centimeter inverse, whereas functional group region lies between 4000 to 400 centimeter inverse. Okay, so that we will see. So this is what we are discussing about the basic about the IR spectroscopy. Now if we see some of the bonds and their vibrating frequency, here we can see that the triple bonds are there, that these two are the triple bonds, then they are vibrating at a higher frequency as compared to the double bond, and which are still vibrating at a higher frequency as compared to the single bonds. Okay, so this is the one point which I want to tell you, that because triple bond are stronger, so they are vibrating at the higher frequency, as can be indicating from this formula, that they are having the higher spring constant, or the this is also called as the force constant, or the spring constant also, it is called as the spring constant also. Spring constant also. Okay, now so double bond will be having higher force constant or the spring constant, so therefore it is vibrating at higher frequency than the double bond, than the single bond. Now if we see that OH bond, if we compare these two OH bond, this is of alcohol and this is of carboxyl group. Carboxyl group. Okay, now in carboxyl group we know that there are two hydrogen bonding which happens between the two carboxyl molecules, so this bond is weaker, so it is vibrating at a lower frequency as compared to that of alcohol. So in alcohol also hydrogen bonding is there, but in carboxyl group there are two hydrogen bonding between the two adjacent molecule of carboxylic acid. So they will weaken this because of the hydrogen bond formation. This OH bond will become weaker, and then this will be vibrating at lower frequency. Now if we compare NHCH and OH, so if we compare OH with that of the any other bonds, CN we are comparing with CH. Here OH, this is having OH. Whenever hydrogen atom is there, they are vibrating at higher frequencies. Why? Because hydrogen atom is having lower atomic mass. So since it is having lower atomic mass, so it is inversely, frequency is inversely proportional to the atomic mass. So this OH will be vibrating at a higher frequency. NH is vibrating at higher, CH is vibrating at higher frequency. But since NH is less polar, so it is vibrating at lesser frequency. That is bond is weaker. Whereas CH is still less polar, so it is still at lower frequency. That is mean to say that it is vibrating at still lower frequency. That is 3300 to 2700 centimeter inverse. So this way we can from this formula we can predict the strength of the bond and also the intensity of the IR radiation which is being absorbed by the bond. Now we see what are the factors which affect the IR absorption. There are some factors we will quickly discuss. We already know also, but then we will quickly cover it. One is bond order. So higher the bond order, more is the strength of the bond. So triple bond is having a higher bond order. That is to say that is having higher force constant, spring constant, and therefore very higher frequency will be there. That we have seen here also. Then compared to the double bond, then compared to the single bond. So single bond is having a lower spring constant, lower force constant. So it will have be vibrating at lower frequency. That we can see from here. Now second point is atomic mass. I have told you that if a hydrogen atom is attached to any molecule, then it will vibrate at a higher frequency because hydrogen atom is having lower atomic mass. That is, the reduced mass will be lower, and then frequency it will be absorbing the higher frequency. And then if similarly if the atom attached is of higher atomic mass, then obviously the vibrating frequency will be lower. As we can see that here CN and CO, we can see here that if the atomic mass is that is higher, then vibrating frequency will be lower. Okay. Now coming to hydrogen bonding. So hydrogen bonding case, I have already told you that in case of carboxyl group, say if this is a carboxyl group, so there are two hydrogen bonding which is happening here. So one hydrogen bond, two hydrogen bond. So this weaken this OH bond, and hence this because of this weakening, what happens is that the OH group of the carboxyl group will vibrate at a lower frequency because more is the strength of the hydrogen bond here, and then more weakening of OH bond will take place here, and then so this carboxyl OH group of carboxyl will vibrate at a lower frequency, whereas OH group of alcohol group will vibrate at a higher frequency. Because of this happens because of the hydrogen bonding, which makes the OH bond as weaker, and then thereby decreasing the frequency. And coming to the hybridization can be sp3 sp2 sp1. So ch3 ch3 sp3 hybridization, ch2 ch2 sp2 ch triple bond ch, that is sp1. So obviously this bond is stronger, as we have already seen. So here if you see here, that is, it is like so here we can see that sp hybridization will have triple bond, whereas sp2 will have two, that is ch2 ch2. That is here we have sp2 hybridization, that is carbon atom is having sp2 hybridized, and this here ch3 ch3 sp3 hybridized. So as already seen that this bond is stronger, so obviously this will be having the higher absorption frequency compared to ch2 ch2 bond, and then the ch3 ch3 bond will be have the least IR frequency absorption among the three. Now the last effect is the resonance and inductive effect. So here if we compare that, we have this aldehyde group here, then ketone group, then we have here ester group, and then we also have the that amide group. Now here in this case resonance is not possible, so it is vibrating at 1725 centimeter inverse. Then ketone group, again this is not resonance is not there. So although there is electron donating group is there, so it will weaken this bond, and then it is vibrating at a lower frequency. And amide group again here, that is electron donating group is there, so again there will be resonance here, so this bond will get weaker, so it is absorbing at 1675 centimeter inverse. But here if you see that this is a methoxy group and this is more electropositive as compared to this nitrogen, so that is mean to say that less electronegative as compared to the nitrogen, so it will again it will not decrease the charge, but here it will strengthen this bond. So this bond is more stronger, so it is vibrating at a higher frequency, that is 1735 centimeter inverse. So that is mean to say that if resonance is there and electric effect is shown in the bonds, then they can reduce the intensity of the bond because of this resonance here and non-resonance here. Because of the resonance effect here, we can say that the CO bond is weaker, that is absorbing at a 16, 17, 25 centimeter inverse frequencies, whereas in this case, since RCHO, that is aldehyde and ketone group, no resonance is there, so they are vibrating at a higher frequency. That way we can conclude that if resonance effect is there, that is a bond is there, a compound is there where the resonance effect is shown, then that may reduce the bond strength of the C double bond O if there in the structure. Thereby it will absorb the lower frequency as we can see from this formula. So these are the factors on which the IR absorption depends, that is frequency of the IR absorption depends. So one is bond order, atomic mass, hydrogen bonding, hybridization, hydrogens, and inductive effect. Okay, so as I was discussing in the previous slide, that electromagnetic spectrum is nothing but if we are arranging the electromagnetic radiation in the increasing order of their wavelength or decreasing order of their energy, then it is called as the electromagnetic spectrum. And infrared region lies here, and infrared and that is visible, and UV region is having a lower wavelength as compared to the IR wavelength, whereas microwaves is having higher wavelength as compared to the wavelength of the IR radiation. Now so here we can see that visible and UV radiation bring about the electronic transitions, whereas IR radiation bring about the molecular transition as well as the vibrational transition. That is, it brings about the rotational, it affects the rotational energy levels, also the vibration energy levels. So we know that in a molecule, apart from having electronic energy levels, we will have the vibration, because atoms, that is bonds or the functional groups in a sample or in a compound is vibrating at a particular frequency, so they are having definite specific energy vibration energy levels. Similarly, atoms around the atoms are also rotating around their axis, so they also possess the rotational energy levels. So if we can draw the electromagnetic, that is we call it the energy level diagram of molecule as well as atom, that we can you can see in the spectroscopic lecture which is there in this channel. So we can draw very easily the energy level diagram of a atom or also of a molecule. In molecule we have electronic energy levels, molecular energy levels, as well as the vibration energy levels. The IR radiation will bring about the changes in the transition in the rotational energy levels as well as in the vibration energy levels. That is here, but to mean to say that near IR lies between 14,000 to 4,000 centimeter inverse. Mid IR region lies between 4,000 to 400 centimeter inverse, whereas far IR region lies between 400 to 4 centimeter inverse. Whereas microwaves is having higher wavelength, that is it is having it's having wave number. This is called the wave number, that is less than 4 centimeter inverse. Wave number is nothing but the number of waves per unit wavelength, how many waves are there. So in 1 centimeter, how many waves it is covering, that is known as the wave number. Now generally wavelengths from 0.8 to 100 micrometer. So sometimes they will ask in micrometer, sometimes they can ask in the wave numbers also, that is centimeter inverse. So IR radiation generally ranges from 0.8 to 100 micrometer, that is used for the IR spectroscopy. Now near IR is having 0.8 to 2.5 micrometer, mid IR is having 2.5 to 15 micrometer, far IR is having 15 to 100 micrometer. Now typically it is the IR radiation is divided into 3 categories as already told: NIR, MIR, and FIR. and that is mostly that is these are the NIR and MIR that is used in vibration spectroscopy. FI is not much used, not having application, whereas near and mid infrared is mostly used. And if you see the in terms of the centimeter inverse, near infrared region, as also already mentioned, that ranges from 12,500 to 4,000 centimeter inverse, whereas mid IR region varies from 4,000 to 100 centimeter inverse. Now MIR further can be divided into two regions, that is one is the functional group region, and that ranges from 4,000 to 1,400 centimeter inverse. Another is the fingerprint region, that ranges, which is a complex region below 1,400 centimeter inverse, and it's ranges from 1,400 to 400 centimeter inverse. And then if the fingerprint region of any two spectra of any sample or any compound matches, then we will say that these are the compounds are the same. So that is why it is called as the fingerprint region, right? Like each and every human being is having unique fingerprint. Likewise, a fingerprint region of any two compound matches, then this indicates that both the compounds are the same. And even if the functional group region matches, we can only say that okay, functional groups are the same, but definitely the compounds or the sample are not the same. Okay, so near and mid IR regions of the spectrum are most useful for quantitative and qualitative analysis of food. So we can use these regions both for the quantitative and qualitative analysis of foods. Now infrared radiation can also be measured in terms of its frequency. So as I've told you that wave numbers is also there, and also we can measure them in terms of frequency, so which is useful because frequency directly related to the energy of radiation by the Planck quantum theory, that is equal to h nu. H is the Planck quantum constant, that is Planck constant, which values is 6.6 into 10 power minus 34 joule second is the energy of the system, and v is the frequency in hertz. So frequencies are also commonly expressed as wave number. Okay, so here we can see that we can express the radiations, that is the wave numbers, wavelengths, that is in terms of wavelength or in terms of frequency. Anyway, we can express, because we know this E equal to h nu, and this is equal to E equal to hc by lambda. So we can write it in this form also, in the lambda form also. We can write it in the form of wave number also. So we can express the wavelength either in terms of frequency or in the terms of wave number from this Planck quantum theory. Frequencies are commonly expressed as wave number, that is frequencies can be here, because frequency can also be expressed in wave number, that is 1 by lambda in centimeter, that is 10 power 4 divided by lambda in micrometer. Okay, so we can express usually internationally the wave numbers are represented, that is the spectra, FTR spectra is having wave number at the x-axis instead of the frequency or the wavelength. We will have mostly the wave number. Now if we say, as I have already told, that chemical bonds in analytic molecules, they are constantly vibrating, they are vibrating at a particular frequency, then there can be stretching vibration or there can be bending vibration. See, if bending vibration, if there is more than one single bond is there, and then stretching vibrations are, each and every functional groups are showing the stretching vibration also, and also bending vibration also. And under bending vibration, we will see that there is twisting, scissoring, rocking and wagging, and then vibration of the bonds can be symmetric also, asymmetric also, that also we will see. And then motion of the bonds can also within the plane or out of the plane, that we are going to see. See here we can see that this is a symmetric stretching. Here in the first, if you see that here it is a symmetric stretching because both the atoms are moving together. So here we can say that both atoms are moving together, so it is symmetrical stretching. And that is atoms are one atom is going one direction, another atom is going another direction, so this is asymmetrical stretching. Then comes the scissoring. Scissoring is like, you know, scissor, the way we are using the scissor, in a similar way bending vibrations will be there, and this is in the same plane. So here it is in the same plane. And here this is rocking vibration, again within the same plane, and then both atoms are moving on the same side together. Here this is wagging. Vaguing means that this is out of the plane vibration, and then here this is showing that the atoms are coming towards out of the plane, that atoms are vibrating out of the field and towards us. Whereas in twisting, here we can see that one atom is coming towards it, at the same time other atom is going inside the plane. So both are the out of the plane vibrations. Vaguing and twisting are out of the plane vibration, whereas scissoring and rocking are in the same plane, that is in the same plane vibration. Okay, so the different types of vibrations are being shown, are being demonstrated by different functional group, by different bonds, and if the vibrational frequency of these bonds matches with that of the IR radiation, then they absorb it. This is the basic principle of the IR spectroscopy. Although there are many possible vibrations are there, but stretching and bending cause the change in dipolar moment. So whichever vibration, whichever motions will cause change in dipole moment, that is dipole moment is nothing but the product of charge and the distance between the two atoms, so that is dipole moment. So if any vibration or motion will cause change in the dipole moment, then only the IR radiation will be absorbed. This is the basic requirement for a bond or for a functional group to absorb the IR radiation. That is, if any vibration has to cause that is change in the dipole moment, then only it will absorb the IR radiations. So note that stretching vibrations, so stretching motions vibrate at higher frequency than the scissoring vibration, indicating that more energy required. So stretching motions vibrate at higher frequency than the scissoring vibrations, indicating that more energy is required. Now we see nuclear diatomic molecules, that is H2 is there, nitrogen is there, oxygen, even if they are vibrating, but there is no IR radiation is absorbed. Why? Because these have zero dipole moment, and also stretching of bonds also is not producing the change in dipole moment. So these molecules won't absorb the IR radiation because their vibration, first of all, that they are having zero dipole moment, and also their vibration is not producing the change in dipole moment, so they are not absorbing the IR radiation. Whereas heteronuclear diatomic molecule like carbon monoxide, hydrogen chloride, they are having the dipole moment and also their vibrations, that is if the bonds are vibrating, and then this will change, this will cause the permanent dipole and stretching of bond will also lead to the change in dipole moment, hence they will absorb the IR radiation. So as already told, dipole moment equal to charge and into distance. So when a molecule absorbs light, it undergoes transition from a lower distance. This is the basic principle of any spectroscopic technique. So in any spectroscopic technique, we know that if a molecule or a atom is absorbing the radiation, then there occurs transition from the lower energy state to the higher energy state. In case of infrared spectroscopy, there occurs transition in the vibrational energy levels as well as the rotational energy levels, as already mentioned. If the light absorbed brings about the changes in the vibrational and the rotational energy states of the molecule, then the transition gives absorption in the IR region. That is meant to say that IR radiations have sufficient energy to bring about the rotational and the vibrational transition in the molecule. The spectrum we are raising is called as the IR spectrum. Okay, now here the same is demonstrated in this figure, that radiations, that infrared radiation, are having low energy and they are only bringing about changes in the vibration energy levels and also in the rotational energy levels, not in the electronic energy levels. So note, in the electronic energy levels, they are only causing transition in the vibration energy levels as well as in the rotational energy levels. Now, as already told, that bonds are vibrating at a particular frequency, and that frequency is given by 1 by 2 pi k into m1 plus m2 divided by m1 m2. So here I have written that this can be also written as 1 by 2 pi root of k by nu, that is where mu is the reduced mass, k is the spring constant or the force constant, and this is also known as the Hooke's law. So to calculate the frequency of the light absorbed, the following equation is used, where k is the force constant indicating the strength of the bond, whereas m1 and m2 are the masses of the two atoms. Now, if there is high value of k, that is bond is strong and it absorbs higher frequency of light, is obvious. So triple bond is more strong as compared to the double bond, as compared to the single bond that we have already discussed. So triple bond will absorb the higher radiation whereas the single bond will absorb lower IR radiation. So a C double bond would absorb a higher frequency of light and than a CC single double bond. Similarly, if the lighter mass is there, because a reduced mass is at the bottom, so if a lighter atom is attached, that is a hydrogen is attached, then of course that vibrating frequency will be higher, because the frequency, that is frequency of IR radiation that is absorbed is inversely proportional to the reduced mass, that is inversely proportional to the atomic mass of the atoms constituting the bond. Now this is how the IR spectrum looks like. So here the graph is between transmittance and the wave number. So wave number will be there on the always on the x-axis, and most of these are given in the centimeter inverse. Most of them they are giving wave numbers in terms of centimeter inverse only, so internationally it is being followed. And then this is mid-IR region ranges from 400 to 4000 centimeter inverse, as already told, and also finger meter regions is 400 to 1400 around, and 1400 to 4000 is your functional group region. So this is your functional group region. Okay, so play to measure intensity. So here it will be wave number, here will be transmittance percentage, and mostly we are keeping here transmittance also. This we can express in terms of absorbance also. And so this peak is indicating that here maximum absorbance is there. These peaks are of higher absorptions, and that is transmittance is lower. So here these peaks are lower transmittance, indicating that they are having maximum absorbance. So a plot of measured infrared intensity per se, a property of light, is called the infrared spectrum. And the fingerprint region, the complex region of the infrared spectrum below 1400 centimeter inverse, is known as the fingerprint region, whereas the characteristic absorption bond of the functional groups are almost unchanged from one compound to the another. So mostly the functional group region are that is the absorption band of the functional groups are not necessarily changed unless there is change in the environment. Okay, now look, we will look about the instrumentation of the mid-IR spectroscopy. So two types of spectrophotometers are routinely used for mid-IR spectroscopy. One is known as the dispersive instrument, other is known as Fourier transform instruments. So we'll discuss one by one in the coming slides. So first is the dispersive instruments. The dispersive instruments use a monochromator to disperse the individual frequencies of radiation and sequentially pass them through the sample, so that the absorption of each frequency can be measured. So here there will be monochromator, and that will disperse the individual frequency of the radiation and sequentially pass them one by one. They will pass them to the sample or to the reference cell, so that absorption of each frequency can be measured. So most IR spectrophotometers are generally double beam instruments, that is we are measuring the taking the reading of the reference or reading of the spectra of reference as well as samples simultaneously. That is to mean that they are the double beam instruments. So here we are using a monochromator, which is dispersing the individual frequency of the radiation and sequentially pass them. Sequentially means one by one through the sample, so that absorbance of each frequency can be measured and ultimately the spectra is obtained. Now if we see about the dispersive instrument, most common IR source. So somebody asked you what type of sources, that is infrared sources, are there. So one is the coil of nichrome wire wrapped around a ceramic core. This also forms the IR source, that is there will be nichrome wire that is wrapped around a ceramic core, which glows when electric current passes through it. So if you pass the electric current through the nichrome wire that is wrapped around a ceramic core, then your IR radiation will be produced. Similarly, a glober, which is a silicon carbon rod across which a voltage is applied. So if you are applying a silica voltage across a silica carbon rod, that also produces the intense IR radiation. So these two are the sources which I have told. Then old spectrometer used NaCl prisms to disperse the radiation into monochromatic components, but modern instrument use the diffraction grating to achieve this effect. So this is about the dispersing elements. So these two are the one is earlier NaCl prisms were used, now diffraction grating or the monochromator is used. So these are the dispersing element. So this line talks about the dispersing element. Now the most common detector is thermocouple. This is now these two lines are of detectors. What detectors are being used? One is thermocouple, whose output voltage varies with the temperature changes caused by the varying levels of the radiation striking the detector. So the radiation will strike the detector, then there will be local temperature changes, and that is being monitored and giving a signal. So whose output voltage, thermocouple output voltage varies with the temperature changes that is being caused by the levels of radiation striking the detector. Now another type of detector is the Galois detector, which is the sensitive detector. So most commonly used is thermocouple, and the most sensitive detector is the Galois detector, in which radiation striking a sealed tube of xenon gas warms the gas. So there will be sealed tube of xenon gas and the radiation that strikes the tube will warm the gas and will cause the pressure changes within the tube, and that is giving the spectra, that is giving the signal. Okay, so these are the Galois detector. Another form of detector is semiconductor detector, whose in this case the conductivity is varying according to the amount of radiation striking the detector surface. So here in this case semiconductor detector, we know that the conductivity will vary. So there is a valency band, there is conduction band, conductance band in semiconductor detectors. So conductivity changes, which is monitored by varying intensity of the radiation which is striking the detector surface. Now next line is about the reference. Why we make use of reference? Because reference prevents fluctuation in the output of the source affecting the data. So any that is mechanical vibration is there, or any electrical fluctuations are there, so that can be minimized, that can be nullified if reference is used. And also this allows the effects of the solvent to be cancelled out, so the matrix effect it can also be reduced. This is more part we have discussed in the spectroscopic lecture that you can see. Okay, now coming to the concept of attenuated total reflectance. So what is ATR? So ATR is based upon the total internal reflectance. So what do we meaning? So we know that whenever light passes from one medium to another, then it gets reflected. Here we can see that, and as the angle of angle of incidence is increasing, angle of refraction is also increasing. Now at a particular angle of incidence, we can see that the angle of refraction becomes 90 degree. Here we can see that at a particular angle of incidence, the angle of refraction becomes 90 degree. So at angle at which this happens is known as the angle of, that is critical angle of incidence. This angle is known as the critical angle of incidence. And then if the angle of incidence is greater than the angle of, that is critical angle of incidence, then incident radiation is completely reflected back. So here if this has increased, that is angle of incidence is greater than the critical angle of incidence, we have seen that the angle the radiation is completely reflected back in the same medium. So this will be medium. The ATR is in this we are making use of crystal, so this is most of the time it is diamond. Okay, so most of the time it is a diamond will be there. So here we can, that is having high refractive index without. So this is known as the total internal reflectance. This phenomenon is known as total internal. So I'm repeating again. So as we can see from the figure that whenever an angle of light enters from a higher medium to that is medium of higher density to lower medium of lower density, then it gets reflected. And then as the angle of refraction increases, the angle of refraction of light is also increases. As the angle of incidence is increasing, angle of refraction is also increasing. At a particular angle of incidence, the angle of refraction becomes 90 degree, and if the angle of incidence is greater than critical angle of incidence, then your radiation is completely reflected back in the same medium. So here we can see the concept. Okay, now this part of the radiation which is entering the sample. So here if you see that the light which extend into the sample is known as the evanescent wave, and this evanescent gives the information about the sample. So we can see that light is also extending to inside the sample, and that is known as the evanescent wave, and this gives the information about the sample that we see here. The IR relation focused on one end of the ATR crystal. At an angle greater than the critical angle of incidence, the radiation reflects back into the crystal. Here we can see the reflector is back and going to the detector carrying some information. The intensity of the evanescent wave decreases exponentially with the distance above the surface of the ATR. So here we can the intensity of evanescence is decreasing as the distance is increasing inside the sample. Now depth of penetration is the depth at which which the evanescent wave intensity decreases to 36.8%. So as this intensity is decreasing to say here it is has dropped to say the intensity is decreasing to 36.8%, then we will say that this is the depth of penetration, the depth at which the evanescent wave intensity decreases to 36.8%. Now, as we told that ATR is making use of the ATR crystal, and most of the time it is the crystals used are zinc selenide, germanium, that is thallium bromoiodide. Okay, so these are the material of the crystal which are being used. Now the refractive index of the crystal should be higher than the sample and should transmit the IR radiation. So this is the requirement of the crystal, that refractive index of the crystal should be higher than the sample and should also transmit the IR radiation. In this case, sample is placed in contact with the crystal. So sample is placed in contact with the crystal, and IR beam passes the crystal through the crystal and slightly penetrates into the sample, and then I've told you evanescent wave I've told you. Now here is it gets reflected internally and partially absorbed by the sample. So it is partially absorbed by the sample and partially reflected internally, and thus carrying the information about the functional groups. Light which extends into the sample is known as the evanescent wave, and this evanescent wave gives the information about the sample. dP is the penetration depth, depends on the wavelength of the light. Onward factor penetration depth depends in the wavelength of the light. Angle of incidence and refractive index of the ATR crystal. So on these three factors, the penetration depth will depend, and generally varies from 0.5 to 2 micrometers. 0.5 to 2 micrometers, it varies between these two. Now coming to advantages of why we are making use of ATR. ATR has simplified the analysis procedure. It is not only saving the time, it is not destructing the sample. There is no pre-treatment of the sample is required. So sample pre-treatment is not necessary. Non-destructive analysis is there, and information of the sample also in the surface can also be obtained as that is being reflected from the surface. Refractive index of the prism should be higher than that of the sample. This is one requirement, and we can say that this is the limitation, that one condition is that refractive index of prism should be higher than that of the sample, and second also that ATR correction is required if you want to resample the transmitters. So ATR correction is also to be applied. So these two are, we can say that there is this requirement which is there, or the drawback which is there, that it also require ATR correction, that if you want to make it the spectral resemblance to the transmitter spectrum, then ATR correction is required. So I've told you that most of the time with the diamond which is used as a crystal. Why? Because there was 100 times reduction will be there in the ATR element cells. That allows intimate contact with the sample, also related to the sample by the requirement. So if a diamond is there, then obviously the elemental size can be reduced, that is 100 times reduction will be there, and since the reduction will be there, then it will ensure that there is intimate contact will be there with the sample. Also the requirement of the sample will be the less. Now then second, the mechanical strength of the diamond ATR. You know, diamond is the toughest, the strongest element known. So mechanical strength of the diamond ATR element allows for compression of the sample. So even if you are compressing the sample to a higher force, then also it can be done for having the intimate contact, that can be done. Then third is that it is resistant to all corrosive and abrasive solvents. So if you want to use abrasive, if you have a sample containing corrosive and abrasive solvent, then also it can be used. It cleans up easily, and because of the low friction coefficient of the diamond, so it also cleans up very easily. It can be cleaned because of the low friction coefficient of the diamond. Okay. So as already told, that evanescent wave is the one that is being extended into the sample, and it interacts with the analyte molecules and loses its intensity. That is what is called as attenuated total reflectance. So there is decrease in the attenuated means decrease in the intensity as it is interacting with the sample, and it returns back to the ATR crystals that we have seen already, and exits from the other end of the crystal, and it reaches to the IR detector and generates the IR spectrum. So this is how the evanescent wave that is exiting from the crystal and to the reaching the detector, and then we have the spectra. Now if you see the designs of ATR cell, there are different designs which are available. That is the traditional vertical piece is there, in which we have the vertical plates will be there, and the sample is being clamped against the vertical crystal. Where we have horizontal type of design in which we have a plate, like here a flat plate will be there, and here this is normally 5 centimeter by 1 centimeter, and we are keeping the sample inside it, and then in this case the upper surface is exposed. So in traditional vertical phase ATR, the thin sample will be clamped against the vertical crystal. So crystal placement will be vertical, and then the sample will be aligned, that is clamped against the vertical crystal. Whereas in a horizontal ATR, that crystal plate will be a flat plate, and that is around 5 centimeter 1 centimeter, and upper surface will be exposed, as we can see here. This is the type of horizontal ATR, and then the cylindrical ATR is there, which is used for mobile liquid. So only a sample will flow from on either side of the cylindrical crystal, and the light will be exiting from the crystal, reaching the detector, carrying the information. So this is the arrangement is called as cylindrical ATR, as the name also indicating. Now there are different configurations of ATR as also available. There is single bounce will be there, multiple bounce will be there, and this single bounce means that is only single internal reflection will be there. In this multiple bounce means multiple internal reflections will be there, and this how these are being produced, and that is depends on the geometry of the crystal, of course, the type of crystals we are using, and also the length. More length will be there, more reflections will be there, and also the thickness also. So this number of reflections depend on the geometry of the crystal, length of the crystal, thickness of the crystal, and also the angle of incidence, at what angle that is incidenting, the infrared radiation is incidenting into the crystal. That also will decide the number of reflections which are taking place from the crystal. Now there is single bounce ATR in which only single internal reflection will be there. There is limited contact with the sample, narrow sampling area. Obvious, there will be weak spectra that will be produced better because there is no enough time is there for the contact with the sample, and then it is suitable for strong observer. So if the compound is stronger observer and then the concentrated solution, obviously that will help, that can give better results in case of single bounce ATR. Now multiple bounce ATR will have multiple internal reflection. Of course it will depend on the geometry of the crystal, length, thickness, angle of incidence, and multiple reflection can be up to 25, but 9 or 11 are most common, which are available. And then greater contact with the sample will be there, broad sampling area, produce intense spectra, and then of course if weak observers or even dilute solutions are there, then obviously we have to use multiple bounce ATR. So these are different configurations, and also we have seen the design of ATR and the configuration we have covered. Okay, now let us see what do you mean by Fourier transform. Now the spectroscopy is called as Fourier transform infrared spectroscopy, and what do you mean by Fourier transform, that we will see now. Actually Fourier transform is a computerized mathematical conversion of intensity versus time spectrum that is generated from the interferogram that we'll see in the coming slide into intensity versus frequency spectrum. So it's simply a mathematical function. Now here you can see the function also, that mathematical function which convert the intensity versus time spectrum to intensity versus frequency spectrum. And what are the basic components of Fourier transform infrared spectroscopy? That is, we call it that interferogram is the heart of the FTR instrument. Interferogram is the heart of the FTR instrument, and then this working is also very important. Now if you say that this is the interferogram which is generated from the interferometer. So interferogram is the output of the interferometer, and it is consisting of it is covering all the frequencies ranging from 4000 to 400 centimeter inverse, covering 9000 frequencies. So it is having modulations of all the 9000 frequencies which is generated by the interference of the different frequencies, and we will have the background signal also, we can have the sample signal also, and then the mathematical function Fourier transform will be Ly to convert optical path difference or the time domain to the frequency domain, that is converted to the wave number here. So this is background and this is for the sample. Now if the spectral subtraction is there, if the background is removed from the sample, then we will have the actual spectra of the sample. So the actual spectra of the sample that has been obtained. So So FDR uses mathematical process, that is Fourier transform, to translate raw data interferogram into actual spectrum. So that is mathematical transform is the mathematical function which is applied to convert the intensity versus time signal, intensity versus optical path difference, that is signal over the interferogram, into the wave number versus intensity graph of the spectrum. Okay, so now if you look at the major components of the FDR basic components, if we see, so we have a light source, there are different types of light sources. So already we have seen, for example, ceramic. We have seen that if nichrome wire is wrapped around the ceramic core and then electric current is applied, then we will have the IR radiation. So when this source is there, and then we will have a laser also. So laser purpose, laser is there, that is it is having two purpose. One is to have the wavelength accuracy, to ensure the wavelength accuracy, and also to align the optical instrument. So that will be seen in the coming slide. And first is the wavelength accuracy. Wavelength accuracy, and second is to the alignment of the IR radiation to the detector. Then we have interferometer working. I will see in the, will discuss in the coming slide. And mostly the Michelson interferometer that has been used. Then we have sample compartment, and then we have detector. Detector can be of here it is written that indium gallium arsenide detector is there, and then DTGS, that is deuterated triglyceride sulfate detector is there. MCT, that is mercury cadmium chloride detector is there. So working we won't discuss here, but detector is there. The purpose is to detect the signal, obviously to produce the spectrogram. And then we have the processing amount, that generally the computer is there. Okay, so these are the basic components of any spectrophotometer which are required, which is there. Okay, now see what is interferometer. Interferometer, as already told, that it creates the purpose of interferometer is to create the path difference and to produce the interferences among different frequencies. So all the 9,000 frequencies that ultimately will have the interferogram, which will be having the modulation of all the 9,000 frequencies covering from 4,000 to 400 centimeter inwards. So at the heart of every FDR is an optical device that is known as the interferometer. So we'll see that how the optical path difference is created, and then either we have constructive interference or destructive interference, and ultimately we'll have the interferogram. So optical path difference of interferometer related small delta is difference in distance traveled by the two light beams. So how it is generated, let's see in the coming slide. So this is Michelson and interferometer in FDR instrument. So we have light source, we have this is helium neon gas laser is there, that is in the instrument. And then this is actually the interferometer. Within we have the fixed mirror, we have the beam splitter is there, then movable mirror is there. Okay, so this movable mirror is generating the creating the path differences. So all the frequencies that is around 400 to 4,000 centimeter inverse, that is covering 9,000 frequencies are modulated, and the interferogram will be having the information of all the 9,000 frequencies, so representing the all 9,000 frequencies. So that path difference is created by the lambda 2 lambda 3 lambda. So path difference will be created, and then we will have the interferogram. So beam splitter. So here if you see from here, that IR radiation from source, that is collimated by a collimated mirror. So this is a collimator that is collimated by a collimated mirror, and it is directed to the beam splitter. So this is the beam splitter. So this is collimated mirror, and this is a beam splitter that is directed to beam splitter. So beam splitter divides IR beam into two beams, 50% reflected to the fixed mirror. So 50% will come here, and 50% will go to the movable mirror, transmit to the moving mirror. Now when both beams are reflected and they can recombine here, they will recombine here. So they are reflected and recombined here, and the path difference will be created. Now the path length of the beam, that is fixed for here, it is fixed for the fixed mirror. When movable, it is changing, and that is why interference pattern will be created. Interference pattern will be created, and a recombined beam is then passing through the sample here, and then reaches to the detector, and interferogram is having all the IR frequencies encoded into it, encoding or the modulated into it, encoded into it. That is around how many frequencies are there? 9,000 frequencies, that is recovering 4,000 to 400 centimeter inverse. Okay, now Fourier transform decodes IR spectrum. So the IR spectrum, the intensity versus path difference graph, or the intensity versus time domain graph, which we are it's get converted to the intensity versus that is wave number graph, that Fourier transform with the mathematical function that we have already seen. Okay, now let us see how the samples are handled, or how the samples are prepared for analyzing in FTR spectroscopy. Sample handling techniques that we see now. So as already informed, that all type of sample, maybe gaseous, liquid, solid, all the state of matter can be analyzed using IR spectroscopy. And then if we have gaseous sample simply require, they require little preparation. Beyond purification, if purification is required, then it's okay, otherwise no preparation is required. Simply a sample cell is required with a long path length, that is 5 to 10 centimeter. And why long path length is required? Because gases shows relatively weak absorbances. So simple, there is no pre-treatment is required, no sample preparation is required in case of gaseous samples. Only high path length cell and is required. Then if you see the liquid sample, for liquid samples are the most commonly measured by transform IR spectroscopy using cells with a path length of 0.01 to 0.1 mm. And because quartz and glass absorb in MIR region, so they are not used. Sample can be sandwiched between two plates of high purity salt. It can be sodium chloride, it can be potassium bromide, vitamin calcium fluoride. So they are IR insensitive and can transmit the IR light. So these liquid sample can be sandwiched between two plates of high purity salt, sodium chloride, potassium fluoride, or calcium fluoride. That is, they are having very low solubility. Also calcium fluoride is having very low solubility, so most of the time calcium fluoride is used. Now if you have solid sample, there can be a sample can be prepared in 4 ways. First is by crushing the sample with a mulling agent, and usually nuzole is used, that is highly purified liquid paraffin in a marble or agitate mortar is there, with a pestle, and then a thin film of the mull is then applied onto the salt plates and measured. So thin film is, so in this first method is that to crush the sample with a mulling agent in a marble with a pestle, and then the thin sample of this mull is then applied onto the salt plates and measured. This is first way. And second way is that second method is to grind a quantity of the sample with a specifically pure salt, that is usually potassium bromide, finely, so as to remove the scattering effects from the large crystals. This powder mixture is then crushed in a mechanical die press. So here a mechanical die press is shown, and then to form a pellet will be translucent pellet will be formed, through which the beam of the spectrometer can pass and then analyzed. So this is the second way, that is using the potassium bromide and using the pellet method. This as already told, that we are grinding a quantity of the sample with this specifically pure salt, and this powder mixture is then crushed in a mechanical die press to form translucent pellet through which the beam of spectrometer can pass. Then comes the cast film technique, in this which is mainly used for the polymeric materials. So the sample is first dissolved in a suitable non-hygroscopic solvent such as carbon tetrachloride, carbon disulfide, or chloroform. So the sample is first dissolved, and then a drop of the solution is deposited on the surface of KPR or NaCl cell. The solution is then evaporated to dryness, and the film formed on the cell is analyzed. So this we casted the film, and then we are analyzing. Care is important to ensure that the film is not too thick, otherwise light cannot pass through. This is obviously that we are taking care of that. 15 micrometer is the generally thickness of the film. We used to have more than 50 micrometer, obviously that light cannot pass through. Then this technique is suitable for qualitative analysis. Okay, then last method is the microtomy, that is to cut a thin film from a solid sample, and mostly it is used for the pale plastic products because integrity of the solid is preserved. Okay, so these are the 4 methods for analyzing the solid mass samples. Mean to say that how the samples are handled, and all states of matter, that is solid, liquid, and gases, can be analyzed in IR spectroscopy. Okay, now if we see if we compare FTR and dispersive IR that we have covered just now, then in case of FTR, this is dispersive IR, and then here is FTR. In dispersive IR, we make use of monochromator, and monochromator, what it does, it sequentially passes each and every frequencies to the detector. One by one the frequency will be transferred to the detector. There are slits are there in this case, opening and then the closing slits will be there. Whereas in the case of FTR, we have interferometer, which is producing the interferogram and covering the all the frequencies ranging from 4000 to 400 centimeter inwards. and the working we have already seen. So if we compare FTR versus dispersive IR, then in case of FTR we have only one mirror is in motion. In case of FTR interferometer, we have only one mirror which is in motion, and it produces a spectrum in as little as 1 second. That is, the fast scans are there, that is rapid scan skip speed is there in this case, and no slits in the system to define resolution. So in case of dispersive IR, monochromator make use of the slits to define resolution, but there is no slits are there. And then laser is there, that is to provide an internal calibration system within the frequency accuracy, that is to check the wavelength accuracy and also to align the IR radiation to the detector. And there is no equivalent. That possibility of stray light is very minimal, that is any unwanted light, interfering light which is there, that is the possibility is very less. And sample is further removed from the IR source. So sample is far from the IR source, so thermal problems are not there in case of FTR equipment, because the sample is the further removed from the IR score. Now if emitted radiation is there, that is not with the detector as happens in the dispersive IR. So here we are not measuring the emitted radiation from the sample. Then there is improved signal to noise ratio is the case there in the case of FTR. So on the other hand, dispersive we are making use of large number of moving parts are there. It requires around 7.5 minutes to 30 minutes for one scan. It is having slow scan speed. It requires slits are there to improve the resolutions. There is no internal reference is there for frequency accuracy or the wavelength accuracy. Stray light is there, possibility of stray light is there in the instrument. Thermal problems are there because the sample is close to the IR scores. IR radiation by the sample is viewed by the even the emitted radiations that is from the sample is also detected by the detector. So this is a major broad difference between the FTR and versus the dispersive IR. So now let us see about the applications of mid-IR spectroscopy. Now spectra normally presented with the wave numbers or wavelength plotted on the x-axis. So we have seen the spectra in the case in FTR spectra or IR spectra, we will have wave numbers on the x-axis, and the transmittance or the absorbance will be there on the y-axis that we have seen. Now these frequencies and their relative intensity of the absorption band can be used to identify the specific. We know that specific functional groups are there, they vibrate at a particular frequency, and this enables the identification of these functional groups. And if a substance, whole substance or compound can also be identified by comparing its mid-IR spectrum with the library. This is there in the computer in the software. So that the comparison will be made, and the compound will be identified based on the closest match. So that is also we can identify. This is the qualitative applications of mid-IR. Then common food application include the identification of flavor and aroma compounds, especially when FTR measurements are coupled with the gas chromatography. So we can identify flavor and aroma compounds when FTR is coupled with the gas chromatography, and also it is helpful in the identifying the packaging films. So packaging films can be also be identified whether it is LDPE, HDPE, or polystyrene. What type of polymer material is there, that also can be matched with the library and to the closest match, and that can also be done. Okay, these are the qualitative application actually. Now coming to quantitative application, as I told you that each and every spectroscopy is having one law. Principle is the Copier law only, that is A equal to ABC. ABC, that is absorbance is directly proportional to the path length of the cell, and also the concentration of the analyte in the solution. So that is this is a Beer-Lamberth law, and then this way that is we can determine the quantitatively the concentration of molecules like fat, protein, lactose, and as we are doing it in milk also in FT machines, that for transfer machines are there, milkoscans, lactoscope, all these are the FTR machines, and there we are measuring the concentration of fat, protein, and lactose. And the fat, protein, lactose contents of the milk can be determined simultaneously with one of these instruments. And then for fat is determined the IR absorption at CS2. We are making use of CS2, which having absorption at 3.45 micrometer. CS3 is absorbing IR radiation at 6.85 micrometer, and where CO, that is mostly the glycerol component, that CO is the crystal part of the fat molecule, that is 5.73. It is absorbing the IR radiation at 5.73 micrometer, and also CC can also be used, that is 8.6 micrometer. But most of the time it's the CO group that is being targeted, that is having absorption of higher frequency at 5.73 micrometer. Now protein molecule consists primarily of amino acid units that is joined by in a long chain by peptide bonds, and then NH bonds absorbs IR radiation at 6.5 micrometer. So protein molecule consists primarily of the amino acid units joined together in long chain by peptide bonds, the nitrogen bonds. This is the nitrogen bond of the peptide bond that is being targeted in the protein molecule, which are having higher radiation absorptions at 6.5 micrometer. Now if you see the lactose and sucrose, so they are determined from the higher energy absorption of the hydroxyl and the carbon atom. So this bond COH, so these bonds are there in the lactose with the sugar, and these are absorbing the higher radiation at 9.6 micrometer, and this is being targeted, and we are continuously define the concentration the lactose. And sometimes CC bond can also be targeted, which having absorption of higher radiation at 8.6 micrometer. So just to show that quantitatively we can also determine the fat, protein, lactose using the FTR instruments, and principle is the same, that as the concentration will be higher, so more intensity will be there at the frequencies, and that way we will able to know how much is the concentration. So first we are calibrating the equipment, and then from the models which have been obtained, and then we will able to analyze the concentration of the molecules. So automated version of this equipment can homogenize and analyze several hundred milk samples per hour, that we in the industries these are available. Automated versions are available which can homogenize and analyze several hundred milk samples per hour. So that is why we say that the analysis time is very less in case of FTR instruments. Okay, now let us start about the near infrared spectroscopy. Some part we will also cover about the near infrared spectroscopy. We know that near infrared radiation ranges from the wavelength is ranging from 0.7 to 2.5 micrometer, that is equivalent to the wave numbers of 14,285 to 4,000 centimeter inverse. Okay, so measurement in near IR spectral region and more widely used for the quantitative analysis as compared to the qualitative analysis, which is there the broader application of the IR measurement. So mid-IR spectroscopy is mostly used for the qualitative analysis, whereas a near IR radiation is mostly used for the quantitative analysis. Now several commercial instruments are available for composition analysis of foods using IR spectroscopy, and major advantage of IR spectroscopy is its ability to directly measure the composition of solid food products by diffuse reflectance technique. So this is to be main principle of IR spectroscopy is diffuse reflectance technique that we have to see now. Now what is the diffuse reflectance that we have to see? So when a radiation strikes a solid or granular material part of the radiation, it is reflected from the sample surface. This mirror-like reflectance is called specular reflectance and has a little useful information about the sample, and most of the specular reflected radiation is directed back toward the energy source, so it is not having much information. So it is reflected from the sample surface but having no information. But another portion of radiation will penetrate through the surface of the sample and be reflected off several sample particles before it exits the sample, and thus carrying a useful information. This is referred to as diffuse reflectance, and the diffusely reflected radiation emerges from the surface at random angles through 180 degrees. So any random angles that it will be reflecting at till 180 degree, and that will be having the useful information. We will have the spectra from that. So if you see the instrumentation of the IR spectroscopy, the radiation source in most IR instrumentation is tungsten halogen lamp. So it is different from the MIR instruments, where we are making use of either the ceramic rod is there, that is nichrome wires wrapped around the ceramic core, to which electric current is passed, and then it is generated. Also we have seen the glober also, that source. But here in IR instrument, it is the tungsten halogen lamp with a quartz envelope, and it is similar to the projector lamp, as it looks like the projector lamp. These lamps emit significant amounts of the radiation with both the visible and the IR spectral region. Now if you see the detector, the semiconductor detector are mostly commonly used in IR instrument, with the silicon detectors used in the 700 to 1100 nanometer range, whereas lead selenide detector used in 1100 to 2500 nanometer range. Then most commercial analysts use monochromators rather than interferometers, so they are mostly using the monochromators. Some instruments have monochromator based on the diffraction gratings that allow the measurement to be taken at each wavelength over the entire analysis, and other instruments are dedicated to the specific application and use simply the interference filters to select 6 to 820 discrete wavelengths that can be impeached on the sample. So now actually the diffraction gratings are mostly used, not the interference filters. The filters are selected to transfer wavelength that are known to be absorbed by the sample constituents, and then whatever filter with the wavelength which we know that it will be absorbed by the sample, so that accordingly we will choose the filter, and the instrument instead filter one at a time into the late wave to directly individual the wavelength from the sample. Obviously these are traditional system and not more used, so mostly used are the diffraction gradient. And if you compare monochromator and interferometer, it is the monochromator which is mostly there in these type of instruments. Now if you see the applications of IR spectroscopy to food analysis, this technique is widely used for measuring. We can measure moisture, protein, lipid, starch in grains, cereal products, oil seeds. So mostly the solid IR spectroscopy is used in to analyze solid products. Principle is diffuse reflectance. IR spectroscopy can also be used applications such as moisture, protein, fat in meats, and lactose, moisture, protein in milk powder can be determined. Moisture, fat in cheese can be determined. Moisture, fat, protein in egg products, total sugars and soluble solids in fruits and vegetables, and then the sugar content of the corn sweeteners. So all these are the application of the IR spectroscopy in relation to the food analysis. Now if you see the advantages of IR spectroscopy as a whole, so it is a fingerprint technique. So fingerprint region can be used as fingerprint technique and helps in determining the specific compound or functional group. The spectrum of an unknown compound can be compared with the standard exactly like the fingerprint, that we can match with the library and we'll be able to know the which is the compound, what is the sample. So it characterizes the purity of a compound by comparing the sample spectrum with that of the pure sample, and impurities are readily detected with the access bands. So purity of the compound can also be determined. So if impurities are there, then obviously the extra bands will be there in the spectrum. It helps in the characterizing the new compounds, so hold together new. So if we are conducting R&D study, then we can characterize altogether a new compound. The various steps involved in isolation or preparation can also be studied by IR. So when we are isolating something and then preparing it, preparing some compounds or some substances or some reagents, and then during the preparation also this IR can monitor the changes which are happening. So both organic and inorganic compounds can be studied, whether they exist as volatile gases, liquid or solid. So all the three states of matter can be analyzed in IR spectroscopy that we have used. But what are the limitations? It is not effective for mixture of compounds. There will be overlap. So mixture of compounds are there, then obviously the overlapping will be there of the spectra, and then interference will be there. There is no lack of this suitable transparent solvent is not there. So no single solvent is available to cover a wavelength range. So there is no single solvent is available to cover wide wavelength. Molecule must be active in higher region. The one of the most important in higher region, that is to say that it should have the dipole moment, and then there should happen change in the dipole moment if the bond, if the functional group is vibrating, then it must cause change in the dipole moment, then only your molecule must will be active in higher region. And second, that mostly it is used for the covalent bonds. So electrocovalent bond is there, that is for example NaCl cannot be determined in IR spectroscopy. So and also NaCl, if you see that it is having a electrovalent bond, it is an ionic bond, so that cannot be determined. And also the vibrating frequency of the NaCl is not falling in the range of the IR spectroscopy, so that way also it cannot be determined. So molecule must be set. This is the limitation of the IR. Now if you see the advantages of FTR in food analysis: rapid screening tool for material identification or qualitative analysis. Rapidly we can do it. That takes hardly 30 seconds. Simple Cook measurement technique applied across all phases of the product life cycle, including design, manufacture, quality control, and failure analysis at all the phases of product life cycle. This FTR equipment can be used. It may be designing, manufacturing, quality control, and failure analysis. Everywhere it is used. meaningful data of the product at low cost and high speed. So cost, high speed is there, low cost the meaningful data we are obtaining. Small quantity of sample is enough to provide, not like that large quantity of sample is required, and so non-destruction of the sample is there. Versatile is a tool that can be used almost any kind of solid of the physical state. So solid, liquid or gas, all type of the sample can be determined using IR spectroscopy. Various sampling accessories are available with a variety of accuracy. So various sampling accessories are available. ATR we have seen, like ATR, and also different types of ATR are there nowadays. Different designs, multi-bounce, single bounce, or that is horizontal type, vertical type ATR. Different types of accessory is there to cater to the different types of the sample. And it is easy to operate and obtain. We can no skill is required. That obtained personnel is not required in the case of FTR analysis. Now also we can place the IR analyzer during process monitoring and control, and this can be placed offline. Offline means away from the process stream equipment that is in the QA lab. In lab, if the equipment is there, then we will call it as offline. The at-line means nearby process that sample can be removed, and that lab on the RMRD, that is sample is removed and then taken to RMRD, that is raw milk reception dock, and then we will say it is at-line. And then online means that is side stream will be there of the main process stream. So main process stream is there, and to the side stream a loop is there in the side stream, and loop will be there. It is there IR analyzer. Then we will say that it is has been placed online. Inline means that is interface to the process stream, that is it is in the mainstream itself. So we will say that the placement of IR analyzer is inline. So any of the way we can place the IR analyzer in order to have the process monitoring and the control during the processing of the product. Okay, thank you.